class. Welcome to day one of online learning. I know this is going to be way more exciting than meeting in person, but we're going to make it work. All right, if you haven't seen the announcement yet for this week, there's going to be a little bit of an extension on, as opposed to our originally planned guidelines and future guidelines for these weeks online. All right, so this week, assignment's not going to be due until Monday. I'm going to be available Thursday and Friday. But typical week, what we're going to do is Monday's going to revolve around lab, which is going to have some sort of video, activity, article, whatnot for you to check out. Discussion due the following week. Tuesday, I'm going to release the lecture for the week. This lecture is going to be a combination of Tuesdays and Thursdays material, so it's going to be a little bit long, but you have plenty of time to get it done, okay? Because that way, Thursday, I'm going to be available if you want to reach out and schedule a Zoom call, phone call, email, whatever you got to do to ask me questions, get any kind of feedback, or if you just want to kind of link up and review some stuff, let me know. Thursday is going to be available for any kind of interaction that you might need. So what we're going to cover today is we're going to get into chapter 1 from the book, Forces. Everything we've talked about so far in the semester has been around anatomy, movement, things like that. Now we're going to start getting into some more biomechanics related topics. So this is chapter 1 concerning forces. This is going to sort of lay the premise for some of the future chapters to come. So please take your time, pause this, take notes, write down any questions you might have, reach out to me. I'm going to do my best to deliver this in a concise method so that way it doesn't drag on too long, but there's also a lot of explaining I got to do. So bear with me here. I'm not getting any interaction, so you got to let me know what I'm not covering enough. Chapter 1, forces. So we are constantly subjected to forces in our everyday life. A force is a push or a pull. Remember, when an object exerts a pushing force, we are subject to compressive internal forces. When we do a pull, we are subjected to internal tensile forces. So remember that when we talked about pushes and pulls in class already, a push gives us compressive forces squishing together, a pull is tensile forces pulling away. Okay, it's exerted by an object on another object. The law of action-reaction. If I exhibit a push into an object, that object is going to push back with equal and opposite force. And forces accelerate or deform an object. If you are not aware of the equation for force, here you have it now. Force equals mass times acceleration. So in biomechanics, in physics, we use the word accelerate. So we're going to be using positive and negative acceleration. The word deceleration does not exist, so keep that in mind. So forces are important for motion because what we do is we manipulate these forces to achieve the desired effect that we're looking for. So we can use these to start or stop something, change of direction, or maintain balance. Remember when we talked about center of gravity over base of support equals balance? Center of gravity is a force. Gravity is acting downwards on that body. There's a picture of your balance right there. Action forces going down into the ground, reaction forces coming back up through her hands. So when we start talking about forces and we draw them out and we're kind of creating a picture, we think of forces as a vector. So we've got our coordinate system, up is positive, right is positive, and then we've got negative going the other way. So think about just your normal sort of graph that you'll look at. We're only going to be dealing with two-dimensional forces in this class, no 3D stuff. So a vector measure is going to be shown by an arrow. Okay, the way that these arrows are going to be laid out is the length is going to tell you the magnitude. Where the arrow is pointing is going to show you the direction. And then the point of application is going to be where that arrow starts. So if you take a look at this guy on the screen, where that blue arrow starts, where his foot is on the ground, that is the point of application. The direction that arrow is pointing is up and to the right, so it is going to be a positive vector. And then the magnitude is the length of the arrow. All right, so pretty straightforward there. That is a force vector. The types of forces our bodies are subjected to are internal forces and external forces. Internal forces are going to be joint forces, so our joints pushing together, sliding together, pulling apart, things of the such, and muscle forces. So what a muscle force is is that center of the attachment of the tendon through the line of pull. Okay, and that is a muscle force acting internally in our body. But internal forces alone cannot cause the body to move in space. So all our muscles do is allow our joints to move, but we need something else to help us translate in space, aka gravity, the ground, whatever we're pushing off of, or whatever we're using to exhibit force. External forces. So these act as a result of our interaction with the environment. Internal forces act inside our body. External forces are outside of our body. Pretty simple to remember there. Okay, non-contact external force of concern in this class is going to be gravity, okay, aka the force of our weight. On here, we're going to show you how we calculate force from our weight. Okay, so this acts to our body's center of mass. Of our mass, which this guy right here is 91 kilograms. We're going to multiply that by the acceleration of gravity, negative 9.81 meters per second squared, and that's going to give us our force due to gravity. All right, so this dude is exhibiting negative 891.73 newtons down into the ground when he's just standing still. Change mass to force when it's subjected to gravity. Okay, remember this equation. Some of the questions coming up here, we're going to be doing that same thing. Another type of external force that we can talk about are contact forces. Ones that we won't really discuss in this class are air and water. It's a little bit beyond the scope, but things that we will talk about are going to be reaction forces, such as perpendicular forces, such as us pushing down into the ground, pushing into a wall, anything that's acting sort of in that equal and opposite pushing direction. And then friction forces are acting in parallel. So you can think about something sliding together is going to be a friction force. Okay, perpendicular force, pushing, friction force, sliding side by side. Showing you external forces or external contact forces. Red arrows, these are our action forces, what we are putting into the environment. Reaction forces, that ground pushing back up into us. Our perpendicular force, okay, this is the direct result of our gravity acting downwards. And then parallel force, this is our friction force present between our shoes and the ground. So as you can see, the result of that perpendicular force and the parallel force, okay, our contact force and our friction force are both going to add up to equal that reaction force going into the ground. If we did not have any friction force, that means we'd be going straight down into the ground. Or say if we did not have very good traction, we wouldn't be able to push at an angle off of the ground very well. So we need both of those. We need a force going down, friction to keep us stuck and not sliding out from underneath us. Here's another example here. The action force, reaction force, coming from a combination of that perpendicular and parallel force, okay, or normal contact force and friction force. Now, action, reaction, parallel, same thing. Reaction, perpendicular, parallel. Friction, talking about parallel to the contact surface, and this is opposite of motion or motion tendency. So when we are sliding that way, friction is coming this way. For friction is going to be friction is equal to mu, which is that U-looking shape right there, times the normal contact force. Okay, mu is given to us, it is calculated, or we can solve for it. There's no value to it. It's not like newtons or kilograms. It's just mu. And then we're going to actually label that normal contact force as R from here on out. Okay, so friction force equals mu times R. Okay, this is based on the material properties of the objects sliding against one another. Here's a little table to give you some examples of it. So you can imagine that metal on metal might be able to slide a little bit better than maybe wood on rubber or something of the such. So check out those examples, see if it makes sense. Another example would be metal on ice. Metal on ice is going to slide very well versus maybe rubber on concrete is not going to slide very well. So rubber on concrete is going to have a higher coefficient, and then that metal on ice is going to have a lower coefficient of friction. Normal force affects friction force. So as we know, these are directly related. The higher normal force that we have pushing into the ground, the more friction is required, or the more force is going to be required to move that object, or the more friction that's going to be present. Friction is not affected by surface area. Don't forget that. So when I show you these two pictures here, you should understand that both objects are going to require the same amount of force to push, regardless of how much surface area is touching the ground. They both have the same normal force going down into the ground. They are both 1,000 newtons. Okay? They both have the same coefficient of friction. They're made out of the same material. Therefore, both of those force vectors are the same length, same magnitude. Okay? Friction force is the same. Object on the right here has a larger normal force going down into the ground. That larger arrow, heavier object, is going to be harder to push than the one on the left. Surface area does not affect friction. It's just the normal force going down into that object. Okay, this is important. We're going to talk about static friction, dynamic friction. So static friction is the friction that is exhibited between two things not moving. So you can understand that before something starts moving, it's really tough to break. Okay, you go to start pushing something that's on some slides, might be tough, but then once it gets going no problem. This is the limiting friction. Two different mu values for an object, whether it is the mu for static friction, how much force is required to get that thing moving, and then there is a mu coefficient for dynamic friction, or how much force is needed to keep it moving once it's already going. Another word for this is kinetic friction. Really tough, higher coefficient of friction just to break something free, but once it's broken free and it's sliding, mu coefficient goes down, requires less force to keep that object in motion. Okay, friction is important. Okay, we need it to move. If we didn't have friction, we'd be running on a treadmill or like a hamster on a wheel. We use that friction to stick us into the ground. That way we can put a force out at an angle. Footwear is $1 billion industry. Cleats, basketball shoes, whatever. The footwear industry has revolutionized sports. And that's all simply through making adjustments to friction. Time, which hopefully you do, you're probably trapped inside, you got nothing better to do. Check out this video. I'm not going to pull it up right now because I'm not going to waste 5 minutes of this lecture of something that you can do on your own. But check it out, kind of get an understanding of how technology has shaped ice skates in relation to friction. We're going to solve a friction problem. The coefficient of friction between LeBron's shoe made out of rubber and the wooden court floor is 0.67. if he exerts a downward force or a normal force of 1400 newtons when he pushes off the floor, how large is that friction force moving in that parallel direction? First thing we need to do, we need to list out our variables. We don't know the friction force. The coefficient going downward of his shoe, or the static coefficient of friction, I should say, the static coefficient, because he's not sliding, he's stuck into the ground. And R, the normal force, is 1400 newtons acting upwards. Multiply those two together. Friction force is 938 newtons. To do for friction, so we're going to work through one more problem laid out in a different scenario just to show you how you can use that equation to solve in a different way. Going into full screen mode. There you go. Here's what we're going to have. We're going to be in a lab. We're going to be testing out some shoes. So we've got with a force of 400 newtons. Have is, because we want to find what the coefficient of friction is of this shoe with the ground that it's going to be operating on. We're going to solve for both static and dynamic coefficient of frictions. Remember, static coefficient of friction is going to have a higher value because it's tougher to get something moving. Dynamic is going to have a lower value because once it's moving, it's easier to keep that object in motion. So let's say in order to break this shoe free, it's going to require 300 newtons of force to get it moving. 300 newtons. Here, just so we have it. Friction equals time R. 100 newtons. We do not know what mu is because we're trying to solve for this. And we're going to solve for mu. Force of 400 newtons. 100 is equal to 7.5. Or we're going to solve for dynamic mu. Free with 300 newtons. Once it starts sliding, we only need 200 newtons to keep it moving. Our friction force is 200 newtons, which is equal to, we do dynamic mu times normal contact force of 400 newtons. Like I said, dynamic mu is lower. It's easier to keep something moving than it is to break it free. Hopefully that makes sense. So all we solved for here is we were trying to solve for mu. Once we knew what the friction force was, okay, what's the force required, times the normal contact force. How much force is going down into that shoe? All right, so that's just a friction problem laid out a little bit differently here. If you need some more practice, there's going to be some on your assignment. There's also questions in the end of the chapter with answers in the back of the book. So that's friction. Get out of this full screen. Now we're going to start learning how to add force vectors together. So we've talked about external forces. Usually we've got more than one external force that's acting on an object. All right, so we need to know how to add these up together to figure out what's that total force acting on the object. Then we can kind of figure out what's the result that's happening from these forces. Adding these forces together, we are going to solve for what's called the net force. Different ways to add up forces is our collinear forces, concurrent and non-concurrent. We will not talk about non-concurrent forces in this class, but we'll talk about the first two. So these are forces with the same line of action. For example, tug of war right here. They're both acting in the same line. One's pulling this way, one's pulling this way. Okay, we can add up the forces together to figure out what the result is. Okay, if this side is pulling with a greater amount of force, it's going to move this way, vice versa. You understand tug of war. Okay, for these, very simple. We just add or subtract. If you want to determine the result of collinear forces, we just need to add these two vectors together. A way that we can kind of conceptualize this, visualize it, is the tail to tip method. So we take one force pushing, one force pulling, tail to tip together. That's the resultant vector. Okay, you can see that the magnitude is increased. The direction is going in the same way. So all we've got to do is add. That's your resultant vector. You don't need to draw these out all the time, but it's just an easy way to sort of think about it, visualize it, sort of understand things when you're putting it all out on paper. Right here, for weightlifters pulling up on a barbell with 2,226.87 newtons, and the mass of the barbell is 227 kilograms, what's going to be the force acting on the barbell? What I'm going to do is, first thing we've got to do is we've got to convert 227 kilograms into newtons. So remember how we did that. 227 times negative 9.81 meters per second is 2,226.87 newtons. Is equal to the force that's being exerted on the barbell. That means that it is in static equilibrium. Moving. There is no acceleration. When we add everything together, it equals 0. When it does not equal 0, then we're going to get a direction of acceleration from those forces. Okay, but that example that we just showed right there on the last slide, equilibrium, it's not moving. Forces, hopefully those make sense. Pretty straightforward there. Add them, subtract them if they're in opposite directions. Are called concurrent forces. So they don't act in the same line, but they're coming together at the same point, just like that picture shown there. They both come together at the same point, but they're pushing out into different directions. So these are going to require a little bit more math. Can't just add them together. Okay, we're going to get back into some trigonometry. Hopefully you remember all that stuff. Effect of concurrent forces acting at a single point on an object. What we've got to do is we've got to sort of draw out these vectors and create a graph. So we're going to do that tail to tip method, giving us our resultant force right there, that green one. Okay, so applied force, red is just the force of gravity acting down on that shot put. The green force is what's going to be ended up exerted into that from the other two forces. So the same thing we saw on the other slides here, but now they are not acting in the same direction. So if we've got a force going up to the right in direction with a force going to the left, tail to tip. That will be our resultant force right there in the red. Just like a tough time understanding which way a force is going to go when we're adding up concurrent forces. Remember that tail to tip method. We're going to draw a free body diagram. So we're going to draw the object with all the forces acting on it. And we're going to need to create a triangle out of this. And that's where we're going to start using some trigonometry. And we're going to down from one force to figure out what are the resultant forces coming out of that in the vertical direction, okay, or the X or the Y direction. Okay, we'll get into that. What are the effect of the forces coming out of the shot put? This is only going to be acting in the vertical direction because that's the way gravity acts. So we've got newtons, and the applied force that we were given here was that he's pushing into it at 100 with 100 newtons at 60 degrees from the horizontal. So these are the two forces acting on that shot put. So we're going to create a triangle from these forces and then get into solving it. Here's your applied force, force of the weight. We can break down that applied force into X and Y components. When we get the Y component, we can add that as a collinear force to the mass to figure out the total Y. Here, this might be a little bit confusing right now, but once we start working through these, hopefully that makes sense. Before we get into solving for X and Y from that applied force, we need to understand trigonometry. That we need to remember are going to be sine, cosine, and tangent, or maybe you remember them as SOHCAHTOA. SOH is going to be sine of the angle is equal to the opposite divided by the hypotenuse. Cosine of the angle is equal to adjacent side divided by the hypotenuse. And then tangent, TOA, tangent of the angle is equal to the opposite side divided by the adjacent side. Okay. In full screen mode, I'm going to break this down a little bit more, help you paint a little bit of a better picture if you have a hard time remembering some of this trig stuff. We've got direction. We need to break it down. Triangle, opposite from the 90 degrees, and the longest line in the triangle is always the hypotenuse. Right next to it, that is going to be the adjacent side. That's our opposite side. Let's say hypotenuse. Adjacent to the angle. Is on the opposite side of the 90 degrees, largest line in the triangle. Adjacent, next to interest On the opposite side is the opposite. Okay, don't forget that. Opposite, adjacent, hypotenuse. Sine, cosine, tangent. Okay, we're going to be using algebra for finding that unknown variable in some of these coming up problems. When we want to find a side of a triangle, we need to at least know one side and two angles. We'll always know that 90-degree angle. When we want to find an angle of a right triangle, we need to at least know two sides of it. Pythagorean theorem, a squared plus b squared equals c squared. If we know two sides, we can find the third side using that equation. C squared is always going to be the hypotenuse. Don't forget it. All right, that picture in the bottom right there, just breaking it down for you. So we can also take use of the Pythagorean theorem when we're solving for a vector. All right. Solving for the vertical direction from this applied force. We need to know what Fay is equal to. What is the of use the hypotenuse, and we know what, and we're trying to solve for the opposite side. So what we do is we plug in sine of 60 degrees is equal to opposite Fay divided by the hypotenuse. Plug those in, we can solve for Fay, and we get it to 86.6 newtons. Sides of this triangle. So with that, we can either do the same exact step that we did using cosine to solve for Fax, or we can use Pythagorean theorem if you want to do a squared plus b squared equals c squared, since we already know two sides. Okay, the way that we're going to solve it here is we're going to go about it the same way we just did. Ax. Okay, now we're going to do the total of the vertical forces. Remember, we had the force of weight, negative 40 newtons. Our force that was applied into it was up and to the right, so up is positive, so that's why we have a positive 86.6 newtons. Add those together, the net vertical force on that shot put is 46.6 newtons. Linear forces, so we can just simply add them together. So we just solved for. Now we're going to figure out what is the total effect of the horizontal force. We know the hypotenuse, and now we're looking for the adjacent side. Okay, cosine of 60 degrees equals Fax divided by 100, just like we did in the last one. Now we're using cosine. Solve that out. 50 newtons in the horizontal direction. Okay, so now we've solved for Fay and Fax. The total effects of these vertical forces. And what is the total effect of the horizontal forces? This is where we can use that Pythagorean theorem to solve for that green arrow that we saw in the last one. Okay, now we're adding up gravity plus that applied force to give us our resultant force. Okay, the totals in that x direction squared plus the total of the y direction squared is going to give us that net force squared. Okay. For the direction of the resultant force, we can use tangent because we know what the opposite and the adjacent sides are, but we do not know the hypotenuse unless we were to just solve for it right there. All right, so this is how we're going to continue this problem to solve for the resultant force of the angle and the magnitude. let's do a sample problem of our own. So what we've got, it's got a bicep muscle pulling with a force of 800 newtons at an angle of 30 degrees. Equals 800 newtons. Angle equals I want to draw a free body diagram of this. I'm going to do that once we get into full screen mode. We want to determine the components of the muscle force, create that right triangle, draw it all out, and then we're going to use our trig functions to solve. All right, so full screen mode, we are going to solve for force vectors. 800 degrees, angle 30, or force 800 newtons, angle 30 degrees. That side, so we got more room to solve. Let's go. Biceps pulling, 800 newtons, 30 degrees. Now what we need to solve for is we're going to solve for force in the y direction, going up, force in the x direction, going in. Okay? Of y. So if we want to solve for f of y, what we know the angle, the hypotenuse, solving for the opposite. Simple. .30 degrees is equal to opposite over hypotenuse. F y divided by 800 newtons. Solve for that. So sine of 30 comes out 0.5, but I'm going to do some rearranging. So all we're going to do is multiply 800 degrees times sine of 30 is equal to f of y. So I'm going to rearrange this. F of y equal to sine of 30 goes to 0.5 times 800. F of y equals or f of x reason we're going to use cosine because we need to know the adjacent and we have the hypotenuse. Cosine CAH, cosine of the angle is equal to adjacent over hypotenuse. .30 degrees equal to of x divided by 800 newtons. I'm going to do the same rearranging on this one as I did on the one above. Okay, we're going to multiply it by 800, get rid of that, put it over on this side. So that way we have f of x is equal to 0.866, 0.866, if you did that on your calculator, 800 newtons, about 692. Solve for that. Once we solve for f of y, we would have two sides and we can solve for the third. Remember, a squared plus b squared equals c squared, so I'm going to write this out. C squared, c is always the hypotenuse. We can throw in either one of these, a squared or b squared, for 400 newtons. So let's do 400 newtons squared plus b squared is equal to 100 newtons squared b squared. 2 squared is 640,000 plus b squared equals not 640,000. We got 160,000. Squared. We'll subtract 160 equal to 80. Remember, b is still squared. What we have to do, square root of b, square root of 480,000. B, or f of x, is going to come out to 692.82 newtons. I prefer to do this method, cosine, but once you solve for one of them, if you would rather do a squared plus b squared plus c squared, or a squared plus b squared equals c squared, you're more than welcome to. Okay, I like to just keep it simple, stick to this method, less steps. I don't have to do that whole square root thing. Another example, solving for a force vector. We are going to spend more time practicing these force vectors. I'm going to give you some practice questions to work on, probably some examples of how to work these out. All right, these just take practice. If you need to, rewatch this video, pause it, take some notes, review on your trig, make sure you've got a good understanding of these things, draw out the force vectors to understand what directions they're going in and know what you're solving for. All right, this stuff is not easy to deliver online, but I'm hoping that if you guys have any questions, you're going to reach out to me. If we need to, we can do a video call, work out some problems together. All right, just make sure that you communicate with me and practice these problems. All right, more examples. Page 45 to 50 of your textbook has some questions. And then on page 399 to 400 are the answers to those problems, so you can check your work. All right, that's all I got for you today. Check out all the resources available on Canvas. Pause this, take notes, write questions, be in contact with me. Good luck.